In this video, we're going to talk about counts. Whenever you do any aggregation, it's always a good idea to include either a count or a count of non-missing values. That way, you can check that you're not drawing a conclusion based on a very small amount of data. Let's take a look at each flight's average delay time. Not each flight, each plane's average delay time. You can identify a plane by its tail number. So first, let's pull in our library, our NYC Flights 13 dataset, and then also pull in our Tidyverse library. So we've pulled these in, and then we want to look at all the flights that weren't canceled. So I've got some notes here which have all the code written for me already. You can pause the video if you need to take a look at what this code looks like. And we can come back here and plug it into R. What this does is takes our flights dataset and filters out any rows that have a blank departure delay and a blank arrival delay. What that means is essentially the flight was canceled. So when we remove those, we get a smaller data frames canceled. There are about, I think, 9,000 flights that were canceled. So this shows 327,000 rows versus our flights data set, which shows 336,000 rows. So yeah, so it's about a little over 9,000 flights that were canceled. Next, what we want to do is create a data frame that has the tail number and then get the average delay for that plane. So we can come back here, punch that in, and what you see here is it shows the individual plane distinct, the plane identifier, and then the average delay. So you can see there are about 4,037 unique planes. Let's go ahead and graph that to get a frequency of the average delays. So you can see most of the delays are around 0, but there are some planes that have a delay of over 300. That's an average of 5 hours. The story is a little bit more nuanced than that. To get some more insight, we want to draw a scatter plot of flights versus average delays. So this shows by plane the average delay by plane. But we want to add the count of flights in here to really get a better idea of how the delays are distributed based on the number of flights. To do that, we take our next line of code here and we punch that into R. And I forgot the comma here. All right, and now this creates a data frame that has the plane number, the delay, and the number of flights. Now we want to put all of this into a scatter plot to see what the data looks like at that point. So we come in here to our notes, and here's the code to plot this new scatter plot. What you can see is that there's a lot of variability in the average delay when there are few flights. The shape of this plot is very characteristic, whether you plot a mean versus group size. You'll see that the variation decreases as the sample size increases. When looking at this sort of plot, it's often useful to filter out the groups that have the smallest number of observations. So you can see more of the pattern and less of the extreme variation on the smallest group. This is what the following code does. So let's take a look at our last line of code we have here. What this is going to do is going to take only those planes that have more than 25 flights flown. So let's close this, hit this, and you can see here this is a much better, it removes a lot of the noise, and you can see that the average delay is is not 5 hours. It's closer to 20 or 0, and sometimes flights even leave early. So you can see that again, between 20 and 40, there's a good amount of planes, and those are something that we probably ask the airline to look into. So there's another common variation of this type of pattern, and we'll look at that going forward in the rest of this course.